Today we have this really cool nested roots integral. It's the integral from 0 to 1 of the square root of 1 plus the square root of 1 plus x to the fourth power. And a substitution here seems pretty natural. We could let x squared equal the tangent of u. Now this implies that 2x dx equals the squared secant of u du. And this further implies that dx would be the squared secant of u du divided by twice of x. Now x would be the square root of the tangent of u, correct? Now for the limits of integration, if we need x to approach 0, terribly sorry about that, we need u to approach 0 as well. And for x to approach 1, we need u to approach pi by 4. So this implies that the integral I in the u world is now an integral from 0 to pi by 4 of the square root of 1 plus the square root of 1 plus x to the fourth power. Now, x to the fourth power would be the squared tangent, right? And we know exactly what 1 plus the squared tangent of u would be. That would be, again, the squared secant of u, and once again, you have the cancellation of the square and square root functions. Okay, cool. And for the differential element, you have this factor of 1/2, and you have the squared secant of u du divided by the square root of the tangent of u. Now, let's just expand everything here in terms of sines and cosines, shall we? So we can get a nicer looking structure. So we have 1/2, the integral from 0 to pi by 4 of 1 plus 1 by cosine u times sine, no wait, it's square root cosine u divided by square root sine u times the reciprocal of the squared cosine of u du. Okay, cool. And as far as this argument here is concerned, we could expand it or simplify it as 1 plus cosine u divided by the cosine of u. And you have some cancellation happening here as well. So all of this implies that I is in fact 1/2 the integral from 0 to pi by 4 of the square root of 1 plus the cosine of u divided by the sine of u times 1 by the squared cosine of u du. Now this integral looks cool in itself, but we could get something nicer to work with if we express everything in terms of the half angle formulae. So we know that the cosine of u can be expanded as twice the squared cosine of u by 2 minus 1, which implies that 2 times cosine square u by 2 is in fact 1 plus the cosine of u. So that deals with this term quite nicely. And of course, we have the sine of u can be expanded as 2 times sine u times the cosine of u by 2. That is, terribly sorry about that. So this implies that I can write my integral I as 1/2, and that's a pretty terrible implies that sign. Much better. So that's 1/2 the integral from 0 to pi by 4 of the square root of 2 times the squared cosine of u by 2 divided by 2 times the sine of u times sine of u by 2, that is, times the cosine of u by 2. Okay, cool. Now, what about this reciprocal of the squared cosine of u? Well, there's a nice relation between the cosine and the tangent, where the cosine of u can be expanded as 1 minus the tangent of u by 2 divided by 1 plus the tangent of u by 2. So here we have to just square that and reciprocate it. So that means what we have here is 1 plus the tangent of u by 2 divided by 1. It is squared. These are squared terms here. Just check my notes to be sure. Okay, so this is exactly what we have right now. And we have some nice cancellation taking place here. One of the cosine terms is gone as well. So that means you have an integrand expressed in terms of half tangents, or tangent of half angles, tangents of u by 2's. That's what I'm trying to say. So I is in fact 1/2 the integral from 0 to pi by 4 of the square root, and this can be written as the cotangent, so let's just write this as the reciprocal of the square root of the tangent of u by 2 times 1 plus the squared tangent of u by 2 divided by 1 minus the squared tangent of u by 2, all squared, integration with respect to u. X substitution here seems pretty obvious as well. I mean, all we should do is take the square root of the tangent of u by 2 and let this equal to some other variable, let's call it t. And this implies that 1 by 2 times the reciprocal of the tangent of u by 2, and because of the chain rule, we have this squared secant of u by 2 times 1/2 again, du equal to dt, right? Okay, cool. So this implies that the term that we have, what we have here is 1 by the square root of the tangent of u by 2 du. That's all of this stuff. And this equals 4 times dt divided by the squared secant of u by 2, which is 1 plus the squared tangent, and the squared tangent would just be t to the 4th power, correct? Okay, everything seems all right. So that means my target integral now in the orange realm is the integral from, is 1/2 the integral from where to where exactly. We have 0 being the lower limit, and the upper limit here would be the square root of tangent of pi by 8. And I think I should have left some space there, or at least zoomed out. Terribly sorry about that. Much better indeed. So we have the square root of the tangent of pi by 8, and the integrand, and this is your new differential element, right? It's 4 times dt divided by 1 plus t to the 4th power, and you have 1 plus the squared tangent of u by 2, again, that's t to the 4th power, correct? And this is squared. And in the denominator, you have 1 minus t to the 4th power, and that's squared. You get rid of one of these things, and it looks much better now. Oh, I don't need to give it a title. Much better. So this implies that I equals, some nice cancellation here, 2 times the integral from 0 to the square root of tangent pi by 8 of 1 plus t to the 4th power dt divided by 1 minus t to the 4th power squared. And this is quite an integral. My approach here was to use a partial fraction decomposition because that would make things look much easier. And you might be thinking, wow, I actually went through the whole labor of a partial fraction decomposition for such a horrific looking rational function. Well, no, of course not. I just pulled it up from Wolfram Alpha. So after multiplying by 2 and invoking that partial fraction decomposition, we now have an integral from 0 to root tangent pi by 8 of quite a lot of stuff, I might add. Reciprocal of x plus 1 squared. Okay, not half bad at all. 1 by 4 times x plus 1. Okay, that's pretty cool. Minus 1 by 4 times x minus 1. And you think that, okay, we're getting a nice logarithmic structure here, aren't we? And then we have 1 by 4 times x plus 1 squared minus, no wait, it's a plus sign, plus 1 by 4 x minus 1 squared. Yeah, the integrals involved are not difficult whatsoever. They just require lots of computation. And for the first integral, you can look for an antiderivative using a substitution. Yeah, you could just use a substitution of letting x equal to the tangent of some variable phi, and I think you'll find a nice antiderivative and evaluate the limits. Okay, nothing wrong here whatsoever. These two are logarithmic structures, and these two just require an application of the power rule for integration. So I'll leave out the details as an exercise and just present you with this neat looking result that implies that sign looked pretty weird. So we have this cool looking result of I being equal to 1/4 of quite a lot of stuff. We have 4 times root tangent pi by 8 divided by 1 minus the square tangent of pi by 8 plus this logarithmic term. It's the log of 1 plus root tangent pi by 8 divided by 1 minus root tangent pi by 8 plus twice the inverse tangent of root tangent pi by 8. And wow, how could an integral that looked seemingly innocent, I mean, the only catch looked to be a nested radical, but still, this result really is something. This is a result. This is an integration result on steroids. And I hope you enjoyed the video. I'm pretty sure you're not going to enjoy today's homework. But anyway, like and subscribe, share the video to support the channel. Thank you. See you next time.